Hello everyone. So in the last couple of days of labs, we've shown that in a closed, isolated system, momentum is in fact conserved. And conserved, remember, in science means that it stays the same. So we're going to use a couple of different techniques to model the conservation of momentum, a very important idea when it comes to collisions. And we're going to start out kind of in the same way we did with energy conservation. We're going to use bar graphs. And then eventually we'll use equations. But for right now, we're going to try to make a little visual here with a bar graph. So we're going to do two examples today. Example number one, you have a man of mass 70 kilograms and a smaller boy of mass 35 kilograms standing together on a smooth ice surface. Smooth ice means no friction, so that we don't have to worry about outside forces. They push each other apart so that the man now moves away with a speed of 0.30 meters per second, like this. Don't know why he yells, but he does. And what I want to know is, what then will the final velocity of the boy be? Okay, so hopefully everybody understands the problem here. First of all, if we look at a system of man and boy, then this system is isolated and closed. There's no mass leaving the system, and the only really important horizontal forces are between the man and the boy. No friction here. And that means, of course, that momentum is conserved. So we're going to use bar graphs here. Now these are a little bit different in shape and in orientation than they were for energy. And that's because energy is a scalar quantity. There always just was energy, or there wasn't energy. Momentum, however, is a vector quantity and therefore can have a direction as well. So you'll notice here that our bar graphs, instead of being vertical, are horizontal. Pointing to the right would be a bar that would be a positive amount of momentum. Pointing to the left would, of course, be a negative amount. And we're also going to use this little organizational tool here to kind of organize things. So let's go through here our objects in our system. We have the man. The man has a mass of 70 kilograms, and his initial velocity, 0. And if he, because he's starting from rest, and if he has a 0 initial velocity, then his initial momentum is also 0. The boy has a mass of only 35 kilograms, notice half the mass, and his initial velocity is also 0, and therefore he has no momentum. Since these are the only two objects in our system, that means that we have a 0 initial momentum. Now finally, the man still has a mass of 70 kilograms, and he is moving at 0.30 meters per second. But let's be careful here. Velocity is a vector quantity, and clearly in the diagram, the man was moving to the left, and therefore has a negative 0.30 meter per second velocity. Got to be careful to define positives and negatives. Notice in the problem I said speed. If I was being nice, I would have said velocity of negative 0.3, but you know. So that means the man does have a final momentum. Momentum is, of course, mass times velocity, so you multiply these together. He has a negative momentum of negative 21 kilogram meters per second. So notice here the bar is pointing to the left. Here's 0. Because it's negative amount of momentum. Now, on the other hand, the boy, who still has a mass of 35 kilograms, has an unknown velocity. In fact, that's what we want to figure out here, the final velocity of the boy. However, hopefully you've noticed that if momentum is conserved, and if there was 0 momentum initially, there must be 0 momentum finally. And if the man has negative 21 kilogram meters per second of momentum, then to make this a 0 momentum, the boy must have a positive 21 kilogram meters per second of momentum. And therefore the total momentum here is 0, just like here. So conservation of momentum in a very graphic way here. Now, once we know the boy's final momentum, we can simply say his final momentum is equal to his mass times his final velocity. Solve for his final velocity. Plug in our numbers. Our final momentum for the boy was a positive 21 kilogram meters per second. His mass is 35 kilograms, and you get a 0.60 meters per second velocity. Notice it's positive to the right, as we saw in the diagram. And also notice that it is exactly twice as big as the man's final velocity. Why? Because he has half the mass. And as we saw in our explosion lab, It's all proportional when you're starting out with zero initial momentum. Then your two object final momentums have to have equal and opposite momentums, and therefore their masses and their velocities are proportional. So, notice the boy has half the mass, so twice the velocity. Here is our second example. Here we have a bullet of mass 10 grams moving horizontally with a speed of 400 meters per second. It embeds itself in a block of wood, a much more massive block of wood of mass 0.39 kilograms that is initially at rest, again, on a frictionless table, so we don't have to worry about external forces. I want to know what is the final velocity of the bullet and the block after the collision, and recognize here that since the bullet embeds itself in the block, that's the same velocity. So, it hurts to get shot by a bullet. And so there's the situation. Let's watch that once again just because it was fun. So there we go. Now notice here the velocity afterwards is a lot slower than the velocity initially. And you might say, why? Well, hopefully you can tell why. It's because a lot more mass is moving. And therefore, in order to conserve momentum, we have to have a smaller velocity. Now, we could look at this proportionally, but let's go through the bar graph here. As in the last problem, if we call the bullet and the wood our system, then it is isolated and closed, and therefore its momentum before the collision is exactly equal to the momentum after the collision. So here's our bar graphs. Initially, we have a bullet with a mass of, and let's be careful here, our masses have to have the same units. So I'm going to convert the 10 grams to 0.010 kilograms, and it has a large velocity of 400 meters per second. So that means that the bullet has a momentum of mass times velocity, or a positive 4.0 kilogram meters per second. The block, on the other hand, the much more massive block of mass 0.39 kilograms, has no initial velocity, it's at rest, and therefore has no initial momentum. So our total momentum initially is 4 kilogram meters per second. That means our total momentum at the end has got to be 4 kilogram meters per second. So our object here, now we could do the problem two ways. We could say that as we did over here, we could list out the bullet and the wood as separate objects, and then realize that their final velocity is the same because the bullet's embedded in the block. That's in fact how the MOP guy does this. I like to do it this way instead. I like to say that our object is a combo object, a single object of total mass 0.01 plus 0.39 or 0.40 kilograms with an unknown velocity. This way we only have one object to deal with finally, but we got to be careful here that this is the combo object and therefore it has the combo mass. Again, you could do this as bullet, wood, their individual masses, and the same final velocity since they're embedded, right? But it just makes the problem, I think, easier to deal with one problem, or one object, sorry. Now, since the momentum is conserved, isolated closed system, and it had 4 kilogram meters per second initially, the combo has to have 4 kilogram meters per second finally. And just like before, now that we know how much momentum it has initially and finally, we can set that equal to the momentum of the combo. And look what I did here. This is important. You either could put in this number, which is the sum of those two, they got to have the same units, or, to work symbolically, this is the mass of the bullet plus the mass of the wood with the same final velocity. Notice I don't have to put two subscripts here because the final velocity of the bullet and the wood is the same. The bullet is embedded in the wood. Now, like I said, you also could write this as equal to mb times vf plus mw times vf. That would be the sum of the two final momenta, but I like it easier this way. Solve. Plug in our numbers, making sure our masses are the same. That's 4 divided by 0.4, which is, of course, 10 meters per second. Notice, it's more mass that's moving, and so you get a slower velocity since momentum is conserved. This is, in fact, one way you could figure out the muzzle velocity of a gun. Right? Shoot it into something and see how fast that something moves afterwards. Now, one little extra problem here. Let's look at this collision between this bullet and this wood, and let's look at the kinetic energies before and after the collision. Now, before the collision, the only thing that had kinetic energy was the bullet, because only the bullet was moving. And its kinetic energy would, of course, be 1/2 the mass of the bullet times its initial velocity squared, or initial speed squared. Run the numbers through, you get about 800 joules of kinetic energy, 8.0 times 10 to the second joules to 2 sig figs. Now, after the collision, both the bullet and the wood are moving. You could do this problem by saying, let's figure out the kinetic energy of the bullet plus the kinetic energy of the wood afterwards. Or, since they're moving together, we could look at them as one combo object, which again I think is a little more clever and a little cleaner. Plug in our numbers, and we get only 20 joules of kinetic energy. 800 joules to start out with, 20 joules afterwards. So this is not even close to an elastic collision. Anytime one thing embeds itself into another, there's going to be a lot of energy dissipated. So this is a very inelastic collision. Not completely inelastic. It didn't stop, like when you ran a cart into a piece of clay. But it did dissipate most of the energy. 780 of the 800 joules was dissipated in the process. Now, this energy is probably going to be stored as around 98%. Right, of the total energy as dissipated as about thermal and maybe some sound, right? And it deforms the block of wood, right? But mostly it's going to heat things up, right, and deform the block of wood and the bullet. So here's a little proof that this is not an elastic collision, even though kinetic energy is conserved. Hope you enjoyed doing some conservation of momentum examples with bar graphs.